Alright, today what we are going to do is look at solving differential equations where there is a small parameter, and when that parameter is 0, then the equation is easier to solve. So we will use perturbation methods to solve these differential equations. So let us start with this differential equation here, and actually this one can be solved. I am solving this differential equation. Please note this syntax. Initial condition is 1, x of 0 is 1. Only one initial condition is needed because it is a first order differential equation. As it happens, this one can be solved exactly. Maple solves it for me. So here I am, and I substitute this into the expression x of t. That gives me the right hand side, as I've told you before. That's a trick. Okay, I can plot it. When I plot it for epsilon equals 0 and epsilon equals 0.2 in red and blue, so here it is. This is the red one is epsilon equals 0, this one is epsilon equals 0.2. I can in fact make it a bit bigger. I can make epsilon equals 0.4, for example, to see the difference a little more. So there is some difference. Let n be 1, 2. Let n be 2. Okay. So here I am posing a solution of this type. Okay, so here is the solution for when epsilon equals 0, and as epsilon changes, I am posing an expansion of this type. x1 is a function only of t, x2 is a function only of t, and so on. And then what I do is I substitute xa. So I substitute x of t equals xa in the differential equation. I substitute that, then I expand that. After I expand that, then I Taylor expand it in terms of epsilon. Default is epsilon equals 0, and I throw away order n plus 1 terms. Okay, so up to epsilon square will be there. Let's see. There it is. Okay, so now you see again, it is not surprising. In this equation, if you set epsilon equals 0, whatever you get, that is here the terms involving x0. So there is x0 or x0, x1, x2. You see x0 appears non-linearly over here, but for x1 it is a linear differential equation. Over here x0 and x1 appear non-linearly, but for x2 it is a linear differential equation. Okay, so each of these now, for this to be 0 for all values of epsilon regardless of t, what we need is that this thing has to be 0, the coefficient of epsilon to the power 0, the coefficient of epsilon to the power 1 has to be 0, the coefficient of epsilon to the power 2 has to be 0. This is how we have done the polynomial example in the previous lecture, and we will do the same here. Now, because my initial condition is x of 0 is equal to 1, that's my initial condition. So when I come here, you see this initial condition equals 1 means this initial condition is 1, this initial condition is 0, this initial condition is 0, and so on. As many as I keep, all of them are 0. That is why when I come to this part, I see that the solution is e to the power minus t times some constant. To match the initial condition, that constant equals 1. Please do this by hand and make sure you understand. That is why over here I am substituting the solution for that which matches the initial condition, and then after that the initial condition for x1 and x2 etc. For all of those the initial condition is 0. Okay, so here we are. Now what I will do is, this was DEA. In DEA I am substituting x0 of t is equal to e to the minus t and just calling it DEA, and in XA, my approximate solution, I am also substituting x0 of t is equal to e to the minus t. When I do this, here is what remains of my DEA, and here is what I know of my asymptotic solution up to now. Then I will take this one, solve it with initial condition 0, then I'll substitute that, and I'll solve this. So I'm doing that in a loop here. You should learn this structure. So for k from 1 to n, in this case n equals 2, what I am doing is I am pulling out the coefficient of epsilon to the power k, that is temp. I am saying temp 1 is the solution of this differential equation temp, that means equal to 0 default, with the initial condition 0, solve it for xk, that's temp 1. Then what I am saying is in DEA you substitute back temp 1. So when you do it the first time, this will become 0 and x1 will have been inserted here. It's 1. And then whatever is temp 1 that you got, you substitute into the solution also. I am using a colon instead of semicolon here to suppress display, and then I am looking at XA. Okay, so I do that, and that's XA. This is the solution that I have got so far. You will realize this is not the same as this solution, although it can be obtained using a series expansion, which I will show you soon, but it is not the same. Okay, so I've got XA. Now let me plot it. So let me plot it for 0.4. What am I plotting? I am plotting this 0.4 XS, that means the blue solution, and this asymptotic solution. For both of them I am putting epsilon equal to 0.4, and here are the two solutions. If you look a bit closely in this video, if the resolution is good, you may see that there are two different solutions here, red and blue, but it's quite close. Okay, these two are quite close. Now the other thing to see is how does this XA compare with XS. Okay, so when I come here, if I take XS, which is the true solution, remember this is XS, it's the true solution. If I take that and do a Taylor expansion in terms of small epsilon to the same order, then I get this expression. It may look a little different from this expression, but it's not really different, because when I take that and subtract the asymptotic solution and simplify, I get 0. Okay, so now over here let me just show you that instead of 0.4, suppose I use 0.6 over here, then I get a slightly larger, I get a visible mismatch. But then I come here and I can take 4 terms if I want. I mean, not something that we will do for typical problems, but when we are trying to understand, it's a good idea to see. So now I have a longer series and DEA is longer and so on, and then I substitute that and I go there, and that is my XA, so that's a longer expression. But when I remember, let's put it up here so that you can see there was previously a difference, but when I run it now, that difference has become smaller. Okay, but I emphasize, I have told you in the previous lecture also, or the one before, this is an asymptotic series. If I fix epsilon at some value and take more and more terms, it is not necessarily going to be better. But if I fix the number of terms and take epsilon smaller and smaller, it will get very, very good. Finally, in this case, it seems that for epsilon equals 0.6, it is getting better so far, but there are no guarantees. Okay, I am not saying that there are. Okay, now over here, here is the Taylor series for the true solution up to the same order, and when I subtract, it is 0. So here is our first and simplest example of using a perturbation method to solve a differential equation that is a small perturbation of a known differential equation whose solution we know. Okay, so now let's start a different problem. Okay, this problem is like this. DE is diff x of t with respect to t twice plus x of t plus epsilon times x of t. Okay, so what is this? This is a harmonic oscillator, and what has happened is that the stiffness is very slightly different from 1. Okay, let us say the initial conditions are x of 0 is equal to 1, x dot of 0 is equal to 0. Okay, so I can solve that. So I'll say xs is equal to d solve dE, and then x of 0 equals 1, and d of x, note the syntax, equals 0, x of t. Okay, so it solves this for me. It is the cosine of 1 over square root of 1 plus epsilon times t. You are familiar with this. This is the solution. I'll say xs is equal to substitute xs in x of t. Just pull out the right hand side. Okay, the solution. Let me go back and solve this with a series expansion. So I will say xa is equal to, I need to do something with n. I'll say n is equal to 2, and then I'll say xa is equal to add capital X k of t times epsilon to the power k equals 0 to n. This is my assumed form. This is what succeeded for the previous problem, but it is not succeeding here possibly. That is why I am showing you this example. We will see that we run into trouble. Okay. Alright, we do this, then we say DEA is equal to expand, substitute x of t is equal to xa in DE. Okay, so there it is, and it goes up to some number, but what I will do is convert Taylor, and then over here I will say epsilon n plus 1 polynomial. Okay, so now I've gone up to second order. Now you realize that over here the initial condition for this is x is equal to 1 and x dot is equal to 0. That means x0 is equal to 1 and x dot 0 is equal to 0, and this one x1 is also 0, x1 dot is also 0, x2 is also 0, x2 dot is also 0. Okay, so I come here and I say DEA is equal to expand, substitute x0 of t is equal to, and of course the solution for this with initial condition 1 is known. It is cosine of t. Okay. And it sort of gets a bit messed up, but I can clean that by saying collect in terms of epsilon. Okay, so now I have powers of epsilon like that. They are nicely arranged. Here is the problem. This cos of t provides resonant forcing to this harmonic oscillator. This is the problem. Okay, so with trying this approach for this differential equation, and we will see the consequence of this. So what we will say is, of course, I have to also do this. Xa is equal to substitute x0 of t in xa. I have to do that. X0 of t is equal to cosine of t. Let's go back here. Start. Okay, so this is the solution that I have so far. Now I will say for k from 1 to n do, okay, temp is equal to the coefficient in DEA of epsilon to the power k, as we have done before. I will say temp1 is equal to dsolve, and then I will say temp xk of 0 is equal to 0, d of x, note the syntax, is equal to 0, xk of t. Then I will say DEA is equal to expand, substitute temp1 in DEA, and I will say XA is equal to substitute temp1 in XA, and I will say end, and I will suppress display. Okay, that didn't work. That's because this has to be capital N, and we will restart. Okay, and we will say XA. Okay, so here is my solution, and I hope you can see the problem with it. The problem is that the correction is t sine t. If I fix t to be in any range, let us say t is from 0 to 7, and then I take epsilon smaller and smaller, this is a perfectly reasonable thing to do. But I am interested in oscillations. They last for a long time. Okay, so I will fix one epsilon, and then I will look at the solution over a long period of time. And what will happen is that t sine t will eventually become big. It will become so big that epsilon times t sine t will become comparable to this. At that point, my series is no longer asymptotic. Okay. When will that happen? When t is of order 1 over epsilon. Same thing here. You see there is a t, but this t square is even more damaging. So t square epsilon square will be order 1 when t is order 1 over epsilon. So as I start increasing the time, a time will come when this will no longer work. Okay. So let us look at this solution. You will see what happens. So let us say plot, and then let us say substitute epsilon equals 0.05 in excess xa. Okay, right, t equals 0 to 3, color equals red, blue. That should work. And you see that oh, come on, that's working. Okay, but now if I say t from 0 to 30, they are beginning to come apart. You see that there is a very small change here. It's coming apart. And if I say t equals 0 to 70, then bad things are happening. See, the approximate solution is not really working. Over the time period when the amplitude has changed, over that time period, basically this solution is wrong. What is this t square we are seeing? This t square is the one that is here. This problem will not go away if I increase the order. So if I go to order 4, it's going to be worse, not better. Okay, so or it will be approximately the same. Well, I guess, but see, now this one is going down. So if I go to 120, then you see it went down and went increased. It is just junk. Okay, so this, what is wrong with this method? The problem is that the time period of the oscillation has changed. So if I go back, see, let me do this here now for n equals 2, just to show you again. Although the plot is wrong, because that's n equals 2 now. So let me say Taylor xs epsilon 3 or n plus 1. Okay. So this is the expansion of the cosine. Remember, this is xs, this is xs. Okay, that's the true solution. This is the Taylor series of that. Okay, and then let us look at xa, and I hope you will agree that these are the same. You see, cosine of t minus half sine t times t, and the same here, and then plus 1/8. This is just the same as that. This is just the same as that. So in fact, our series solution is correct in the sense that if we hold t constant and take epsilon going to 0, what we are obtaining is in fact the corresponding Taylor series for this problem. Okay, so when the time period of the oscillation changes, we have to have other methods. We can't just have this expansion. This is called a regular perturbation expansion, but we will have to do something that is a little bit different. Okay, so this is the idea I wanted to give you in this example. What we have to do is we have to stretch the time in such a way and insist on a periodic solution. Okay, this happens because we don't know the time period. That's enough for this lecture.